Okay, so we are ready to start our second lecture series. We are very happy and very grateful to Anna Fino from the University of Torino. And she's going to tell us about interplays of complex and symplectic geometry. Thank you, Anna.
Thank you very much. Thank you very much, Claudio, Filippo, and Adriano for the invitation. It's a pity that we cannot be in Levico, but we hope to do this in the future. The free lecture will be about interplay of complex and symplectic geometry. And the idea is essentially to see many generalization of scalar geometry, other considering Hermitian metric, other considering almost Hermitian metric. And the idea is the following. So we will work always in an even dimensional real manifold. And as I say, the idea is to look for interplay between symplectic structure and almost complex structure, or integrable, almost complex structure, so complex structure. And often the problem, the interplay, can be expressed in terms of existence of special Riemannian metric. And many problems can be seen in terms of PDE. And sometimes when you have symmetry is in fact ODE. The idea of the lecture will be to start with the first lecture. We will see the timing condition, that is condition that interplays actually symplectic structure and almost complex structure. And we will see that interplay in the integrable case, so in the complex case. And this will be translated in a special type of metric, pluriclose metric or SKT metric. And so the idea of this first lecture is to see some result, all the new about pluriclose metric and some of the problem. And the second lecture will focus on symplectic Calabi-Yau problem. So again, the timing condition will have a role together with the calibrated condition. And the idea here is to generalize the Calabi-Yau problem, the Calabi-Yau theorem, let's say, in the symplectic case. And in the third lecture, I will talk about balance metric, which are special type of, let's say, Hermitian metric. We generalize Calabi-Yau metric in the sense that, in fact, Calabi-Yau metric can be viewed as a special solution of whole Schrödinger system. So the idea of the third lecture will be to see an overview about balance metric and recent result that I get related to whole Schrödinger system that generalize the Fuyao solution for the system. So let's start from simple things. So the idea is, as I say, let's work in even dimensional manifold, and almost complex structure is just an endomorphism of the tangent bundle, such that the square is minus identity. And for what I mean for integrability, I mean just a Minoio tensor is 0. So I meant that is an analytic condition. So the bracket of two vector field of 1, 0 type is still of 1, 0 type. An important thing that one can do on a complex manifold is that if you consider the differential, then you have a natural splitting of D as a sum of D and D bar. And the condition for D square equal to 0 allow us to define what is called the Dolbeau cohomology. But we will see that also other type of cohomology, like Eppler cohomology, will have a role related to pluriclose metric. Okay.
Anna?
Yes?
Sorry, there is a question in the chat. Maybe Bryce is asking why you are assuming that the dimension of your manifold is 2n.
Yes, because I always assume that there exists other almost complex structure and symplectic structure. So the even dimensional is one of the conditions for such a system. Okay. I hope.
Thank you.
Okay, as in the first talk, in the first lecture today, we talk essentially about Kähler manifold. Here, as I say, we will see generalization of Kähler manifold in two sense. So inside the family, let's say a complex manifold, some complex manifold are more complex, let's say, and in fact, this more complex often is given by the existence of special metric. So we will consider Hermitian metric. What I mean for Hermitian metric, I mean that for any point of the manifold, for any pair of vector tangent vector to the manifold, you have this condition, okay? So this condition essentially say that the G is orthogonal with respect to the almost complex structure. And that's the definition, of course, makes sense when J is integral, not integral, doesn't make any difference. And one can associate to the pair metric and almost complex structure or complex structure a form, a natural form, we will call fundamental form, which is a form of type 1. Okay, and a complex manifold, I recall, is called Kähler if admits an Hermitian metric such that this omega is the fundamental form is closed. So Kähler geometry makes together complex geometry, so J is integrable, and symplectic geometry, because omega in particular is a symplectic form. And very simple example, of course, are Riemann surfaces for complex dimension n equal to 1, all the two forms are closed. And there are two very simple examples, flat in this case, Cn, and the torus, just quotient of Cn by lattice, zeta n. And the first interesting case is the complex projective space with the Fubini-Staub metric. So, of course, the first question one can ask, are all complex manifold Kähler? The answer is no, is yes, if the complex dimension is 1, but the complex dimension is bigger than equal than 2, then you have some necessary topological condition, like the odd Betti number has to be even, fundamental group has to be of particular type, and then you have the formality in the sense of rational homotopy theory. So we have quite rich topological structure. This is not anymore true if you assume the existence of metric which have special property, so compatible with the complex structure, but not Kähler. And one nice result that apply just for complex surfaces, so in this case, the complex dimension is 2, a compact complex surfaces is Kähler if the first Betti number is even. And that's essentially show using the Kodaira classification of complex surfaces. We don't have this result in eigendimension. And let's say one of the more simple non-Kähler example that we will see in the talk, especially in the second one, is just very simple, is the Kodaira-Torson manifold. You can describe this way. So you take a copy of G, which is an important group, and it's simply described as a product of the real Heisenberg three-dimensional group. So just this group of triangular matrix times a factor R. And then you have a copy of a lattice that simply you can take considering X, Y, and zeta, just integer. And that was shown that this real four manifold is complex and symplectic. In fact, a simple example of complex structure and symplectic structure just come from, let's say, linear algebra, because you can work at the level of the algebra of G and just define an integral almost complex structure on the Lie algebra G and a symplectic form on the Lie algebra G. And then automatically you have an induced complex structure and symplectic structure on your compact quotient. This is what is called, I will consider as invariant structure. So every time you have a structure induced by something at the level of the algebra will be invariant. And the homology of this manifold is quite simple, because this is an example of nil manifold. So compact nil manifold, compact quotient of a simply connected group by lattice, and the homology by Nomizu theorem is just the Chevalier-Heilenberg homology of the Lie algebra. And B1 is free because you have free closed 1,4, and it cannot admit a Kähler metric. That's essentially, one can show that because it's non-formal in general for a nil manifold unless it's a torus. So to be compact nil manifold, it means to be a special example of compact locally homogeneous space. And Hasegawa showed that in fact, if you take any complex structure on such nil manifold, this has to be invariant. So it's always induced by a complex structure on the Lie algebra of G. This is not anymore true if you consider nil manifold of Weigel dimension. Okay, let's define now what I will consider as a timing condition. So for a Kähler manifold, we have essentially a symplectic form. The fundamental form omega is closed and non-degenerate, is of type 1,1, as I say, and is positive. So it defines a Riemannian metric. And the Niroyan tensor is 0 because you have always a complex manifold. And it's due to Gromov, the notion of, in general, for almost complete structure on a symplectic manifold to be tape. What does mean? Okay, there is a question, I see. Are there a link between Lie group and Kähler structure? Because they are the Eisenberg I saw before. Okay, in fact, is more general. Of course, you can show, if you work at the level of invariant, let's say Kähler structure, you can work simply on the Lie algebra, but here the result is more stronger because, as I say, there are some topological obstruction to the existence of Kähler structure. So in fact, this is a result by Hasegawa, but shown also by Benson and Gordon. They show that in general, if you take a nil manifold, so takes a nilpotent group by a lattice, okay, you cannot have Kähler because you cannot, your manifold cannot be formal unless it's a torus, because the minimal model of your compact manifold is just given by, let's say, the stereo algebra. Maybe I can use, so you have G, I can, all right, maybe it's simpler. You have G, why it's not working? Before was working, sorry. Let's do, I don't know why now appear this one. Okay, now let's go back here. So you have something like that, G over gamma in general. And what happened for the minimal model is the following. And the Lie algebra G, let's call G star the dual. This is generated by, let's say, E1. In this case, is E1, E3, E4, but in general, you will have 2 and 1, 4. And then the minimal model is just given by the serial algebra generated by E1, E4, in this case, with the differential. And that cannot be minimal, okay, unless the nil manifold is a torus G abelian. Mark one question: do any of the complex structure on M from bi-invariant complex structure on G? Okay, that's. But I think the Eisenberg. So your question, if the Eisenberg times R admit bi-invariant complex structure, the answer is not, because I do this. Because in fact, what you are asking is if you have on your group G J bivariant, so J commute we had, that means that these J's make G complex Lie group, okay? And this is not the case. So it's not cannot admit a bi-invariant complex structure. I hope that I answered the question. So, okay, let's go to the place. Okay, so now we look this taming condition, which is this one. Okay, so the condition is essentially if you take the 1-1 part of omega, this is positive. And in fact, we use this 1-1 part here, okay, to define a natural metric which is compatible with J, with a complex structure, almost complex structure. Okay, complex dimension 2 is quite special because, again, for complex dimension 2, if you have a compact complex surface, let's say, and this admits a symplectic structure, taming J, okay, then automatically your complex surfaces is scalar. And there are two different proofs by Streets. One is given by Streets and Tian. They call also this structure Hermitian symplectic structure in the literature. And they show this essentially using the signature of what is going on for let's say non-killer complex surfaces. And there is also nice proof by Li and Zhang. And the proof by Li and Zhang use essentially what is called the taming con and the calibrated con. I will talk more about the calibrated condition in the second talk, second lecture. And the problem that now I am writing is still open, completely open. So the problem is the following. That's there exists an example of compact complex manifold with complex dimension n bigger than 2, which admits a symplectic form timing J and no killer. This is completely open, and we will see some negative result, some I obtain, some other people, and essentially many of these results are translating the problem in terms of pluriclose metric that I will define in a moment. So the idea is the following. If you consider omega, and then you work considering the 1-1 part, the 2-0 part, and the 0-2 part, and you simply impose the condition the omega 0, then you can translate the condition essentially asking that the del of 1-1 part of omega is the bar exact, is the bar beta if beta is minus the 2-0 part of omega. And the important thing is that this beta is the close. And that's what allows to consider the condition to be pluriclose. For a Hermitian metric to be pluriclose, it means that the bar of the fundamental form is 0. So let's give the definition. Okay, so an Hermitian metric on a complex manifold is pluriclose, or SKT, if the d bar of omega is 0. And that can be defined also in terms of the operator dc, which is just given by this expression. So minus I, d bar minus del, and the condition is just that dc omega is closed. Okay, in the generalization of, let's say, Kähler condition, pluriclose condition, this condition for the fundamental form to be the bar closed, is essentially the only weakening of the Kähler condition, which is linear in the fundamental form. There are other generalizations, but are not linear. And there is a nice result due to Duchamp that essentially will show that for, again, complex dimension 2, so complex surfaces are special because every compact complex surfaces will emit a pluriclose metric. And the general result is the following. So consider a compact Hermitian manifold. Then Paul showed that this is a unique function, it's infinity function, such that if you do the conformal change or your omega and you do the wedge n minus 1 times, okay, this is for the fundamental form to be the Dubois power of the fundamental form n minus 1, 0 is what is also called the standard condition, standard metric condition. So what happened with the conformal change that you get a new metric, let's say, such that the Dubois or the wedge power n minus 1 times 0, and then you have this integrability condition that ensures you the unicity. And that's nice because what happened that, of course, from the previous result, we have that every conformal Hermitian metric structure on a compact complex manifold contain an Hermitian metric, omega tilde, just by conformal change, we satisfy this condition. So for n equal to 2, you can see that every compact complex surface has a pluriclose metric. So of course, an interesting case should be higher dimension, but by the work of Stritzetian, we'll see later, related to what is called pluriclose flow. In fact, the existence of pluriclose metric can be interesting related to the classification of compact complex surfaces. Another result due to Duchamp that essentially when you have a Hermitian manifold, Levi-Civita connection doesn't preserve, right? If it's not scalar, doesn't preserve the complex structure and the metric, but you have a family, one parameter family, a canonic Hermitian connection, so preserving the complex structure, preserving the metric, and essentially the property of this connection can be detected by the property of their torsion. So I will confuse a torsion, like I will, using the metric, considering the torsion like a zero-free tensor field. And inside this family, there are two connections that will be important in our lecture. The first one is the chain connection. And the condition is essentially that the torsion has vanishing the 1-1 component, okay, the torsion, and the bismuth connection, also called Strominger connection for the application in physics. And in this case, you are asking that let's say the tensor here, T, is Q-symmetric in all the arguments, okay, not only in X and Y, but also if you use zeta. And this is what is called bismuth connection. Why introduce that? Because in fact, the pluriclose condition can be interpreted in terms of bismuth connection. Okay, here I just write the expression, how is related the torsion, comparing with the Levi-Civita connection. So essentially, this gives the difference between bismuth connection, chain connection from the Levi-Civita connection. And as I say, the pluriclose condition, that you remember was essentially DDC, omega 0, can be interpreted in terms of the bismuth connection in the condition that the torsion, the bismuth of the torsion, is closed. And another one form that we will use will be the trace of the torsion of the chain connection, which is called in the literature Lie form. And it's just defined by, you take the co-derivative of the fundamental form and then you apply J. And essentially this is the unique one form such that if you do the differential of n minus 1 power of omega, then you get theta wedge omega n minus 1, and we'll see that we will have an important role. Okay, so we talk about pluriclose. metric. Let's see example. Okay, the more easier example that you can get is on an even dimensional company group, real company group. So G will be our compact Lie group. Let's consider the complexification of the Lie algebra G, and let's consider the Cartan subalgebra. So left invariant complex structure on G are in fact equivalent to pairs, let's say, where JT is any complex on T, okay, and P is just a system of positive roots. So essentially, when you want to define a complex structure, you just define the 1,0 part, right? And this is given by the 1,0 part on T, and then the sum of the root space, essentially. And how we get pluriclose metric, we just take the negative or the Killing form on the commutator, GG, and then you extend to a compatible metric with G, which is, of course, positively defined on the Lie algebra G. That's nice because everything is simple, but in particular, the Bismuth connection is 0. So that means that our example, if you look for property related to the Bismuth connection, the example will be Bismuth flat, right? Why the metric is pluriclose? It follows essentially because the torsion in this case is very simple. It's just given using G by the bracket. And this is a closed free form. We will be interested here in non-Bismuth flat. That example are very important, for instance, for generalized scalar geometry. I will not talk about generalized scalar, but provide the example of compact manifold amidst generalized scalar structure. So let's see other examples which are not, just check. Okay, I skip one, which are not Bismuth flat. Simple example you can get considering compact locally homogeneous space. So as before, we consider a compact quotient of a simply connected group by a lattice, and then we consider J an invariant complex structure. So that means that comes from a complex structure on the Lie algebra of G, and I get with Parton-Salomon and Riatti Mezzoni some classification result in smaller dimension for complex dimension 3, a complex dimension 4, and essentially is here there is an open conjecture that we didn't yet prove. If you start with a company manifold and which emit a pluriclose metric, and J is invariant complex structure, the conjecture is that the Lie group has to be special, two-step. That means that the commutator GG is essentially contained in the center of G, and that's still open. And from the point of view of manifold, it means that the total space of holomorphic torus bundle over torus. There are other classification results on compass of manifold, which is analogous of that, just you consider in this case G solvable. I get some result with Fatale and Ugarte. Always you assume either some condition on J or some condition on the solvable group. For instance, this result with Fatale and Ugarte, we assume that the complex manifold is complex dimension free and there's a non-zero holomorphic free zero form. This system will be important for the third lecture. It will be related to the Hall-Ströming system, we'll see. And then recently I get some result with Fabio Paradiso, and in this case, the group G is what is called almost abelian. That means that essentially G is an abelian ideal of codimension 1. And then more recently, there is a nice characterization by Freiberg as one, where essentially characterize two-step solvable Lie groups, let's say, emitting pluriclose metric. And more recently, I get some result with Nicoletta Tardini and Luigi Vezzoni, and that's quite surprising, quite strong. In fact, if you consider just a unimodal Lie group, okay, and consider the existence of left invariant pluricloth metric, and you assume that your complex structure is abelian, that means that if you take G, the 1-0 part, in general, this is a complex, is a subalgebra, okay, or the complexification, but you ask that this one is abelian, then automatically the group forces the group to be two-step. In fact, the nil manifold case is the richer one, admitting in some sense a pluriclass metric, and this is maybe related to the fact that we have this conjecture, so it should be something very strong related that we don't see that imply in fact this condition. Other example, which are not bismuth flat like the previous one, or recently there is a nice result by Alexandra Ottimo, where he considered the existence of pluriclass metric on a Holekhaus-Thoma manifold, what is called OT manifold, which are essentially a generalization in eigendimension of Bombieri Inova surfaces. And the idea here is to take the quotient of, you take the upper half plane H product S time times CT, and then you quotient by an action of U times OK. So the idea is to start with an extension K of Q, and then OK is just a ring of algebraic integer, okay, and Q is, let's say, suitable subgroup of the group of totally positive units, okay, that we will denote in that. So the action essentially of OK is by translation, let's say, and the other one is by rotation. That's the action. And the nice thing here, that Ottiman found that the condition to admit a pluricloth metric is in fact, let's say, topological, because it's something in terms of the Turbety number and the Hodge number H1. So this is not only the case that you have this obstruction related to B3 and H1, and then there is other construction that essentially are again holomorphic Taras bundle, let's say, over Keller manifold. The first case was constructed by Grancherov, Chubrador, and Poon, and is on connected sum of K minus 1 copy of S2 cross S4, connected sum K copy of S3 cross S3. And the way they construct that is to consider a holomorphic Taras principal bundle over a Keller manifold that is obtained doing the complex blow up of CP2 K copy, K times, okay? And more generally, Podar and Tukur consider the existence of pluricloth metric on principal bundle over a projective manifold, where the structure group is either a unitary group, spatial orthogonal, or compact symplectic. And again, they found out that imposing some condition on the topology of the total space, you can get pluricloth metric. One can characterize.
Sorry.
I skip all the time some.
Anna, I have a question. Can I ask?
Yes.
Hi. In these examples of Podar-Tukur, the manifolds have vanishing first in class?
Yes, I mean, there are one, it depends on the group, on the structure group. As far as I remember, for when the group is, I think, unitary, if I am not wrong, the condition is not really that the first chain class is 0, but it's something like C1 square is equal to C2, something like that. If I am wrong, yes, C1 square equal to C2 in the unitary case, and in the case of special orthogonal or compact symplectic, the condition is that the P1 is 0. So the first Pontriaghi class is 0. That's what they show. They show, and the base, of course, is a projective value. So the base is projective value. It would be nice, in fact, on this paper to see if the metric have other property, but I look a little bit, and it seems that I'm not, I mean, they proved existence, but they didn't write explicitly the metric. So I think it would be nice to investigate more the property of this pluriclass metric if they have other property. And essentially this paper generalized what Geranchelov and Pun did more in general.
Thanks.
I hope that, okay. Okay, here I just see some results that I obtained with Adriano. And so of course, one question is, okay, for instance, for Kähler manifold, if you take a Kähler manifold, you apply the complex block at a point or along a compact complex manifold, then the Kähler condition is still preserved. In general, this is not the case if you take any Hermitian metric, but this is true for pluriclass metric. This is what we show with Adriano, and in fact, we apply that to resolution on complex RP4 with pluriclass metric, and this allows to construct new simply connected example, compact example, admitting pluriclass metric. And one can characterize pluriclass condition, timing condition, Kähler condition. The Kähler condition was the first characterization, let's say, due to Harvey laws, or in terms of currents. So here, maybe I will skip a little bit. I will go fast. So we take the space, let's just denote by dpq, the space of PQ form with compact support on the complex manifold. So we just say the topological dual, okay, of this space, and then there will be an element here will be a current of b dimension PQ or b degree n-1, n minus p, sorry, n minus q. And locally, what we will have n minus p, n minus q form with coefficient distribution. And we will talk about reality, just using the duality of the form with the currents, and positive and strictly positive. It was used already in the first lecture. Okay, let's go to the characterization. So the characterization of the existence of Kähler metric is due to, in terms of currents, is due to the famous theorem by Harvey-Lawson. So a compact complex manifold does not admit a Kähler metric if and only if the complex manifold has a non-zero positive current of b dimension 1,1, which is part of an exact current. Alessandrini and Bassanelli, in fact, the second condition was also shown by GD, generalize this for essentially for symplectic form, timing J. The existence of symplectic form timing the complex structure can be viewed also in terms of currents, just saying that if doesn't admit such symplectic form, if and only if as a positive exact non-zero current of b dimension 1,1. And the weaker condition for having no pluriclass metric, or stronger if you interpret in non-existent, is that M admit a positive non-zero current of b dimension 1,1, which is DD bar exact. So all the conditions that we saw, the generalized Kähler condition, can be viewed in terms of currents. And using currents, In fact, with Adriano, we show a result, an extension result. We generalize the extension result by Minaoka for Keller metric. In fact, we will consider complex dimension bigger than 2 if you consider a complement of a point, which admit a pluricross metric, then you can extend to a pluricross metric in the manifold. And everything can be, this extension theorem can be shown essentially using currents, because omega corresponds to a real CT positive current of B degree 1, 1, which is the bar close. So you work, in fact, with CT positive current, the bar close. And to show that, I will just give a sketch of that. You essentially work looking in the in an open ball around the point. You just work on the open ball BNR, removing the 0. Okay, so the idea is to extend that as a current before, and then to get some fundamental form of a pluricross metric in the whole open ball. So the idea, we need just to show that if omega is a fundamental form of a pluricross metric on the open ball, removed with the center, then there is this, let's say we will consider an annulus, so an R between 0 and a small r, and a 114 on the whole ball, such that this extension is a fundamental form of a pluricross metric. We coincide with the original omega, with starting omega, in the complement of the open ball with, let's say, smaller, okay, ball, we can consider 2/3 R. As essentially, as I say, the extension is obtained using previous result due to extension occurrence. The first one is due to Alessandrini and Bassanelli that say that if you take an analytic subset in an open set in Cn, and T is a pluric subharmonic, it means that E, the d bar T is positive and negative current, we will consider T equal to minus omega, so we'll get a negative current of the dimension PP. In our case, we'll consider P equal to 1 on the complement of omega with epsilon. Epsilon in our case will be just a point, so the dimension is 0. Then there is this, what is called the simple or trivial extension, you extend by 0, the coefficient, and T0 is pluri-subharmonic. And that idea is to consider, to extend this as a current in all the ball. And for that, we use a result which was stated before by Siu and then generalized by Bassanelli, essentially. If you take a current of B degree HK on your open ball, and if T is of order 0, that means the coefficients are measured, and E d bar T0, we can show that in fact d bar of T0 is 0. Then you can write T as d del of G plus the bar of H. In our case, T will be here, so G will be H equal to essentially H, with G and H locally integrable function as coefficient. So we apply that, we have this situation, okay? And in fact, what happened that G is moved in all the open ball beside the center, 0, and then at the end we regularize G in order to obtain the d bar close and positive 114. So we can extend the pluricross condition. Now I mentioned some negative results, as I say at the beginning. The first result that is very simple and is related to pluricross metric is, in fact, if you consider, so I reviewed at the beginning, a company manifold cannot be killer, right? So the natural question is, can you have a symplectic form timing J? In fact, we show that this is not possible unless you have a torus. So this is the first generalization. I will skip that. And one can generalize a little bit that, consider instead of G nilpotent, the condition for G to be completely solvable. That means that add X has only real eigenvalues. Okay, and in this case, there is analogous of what I reviewed at the beginning for compact solid manifold of completely solvable type, because again, you have a current structure if and only if it is a complex torus. So okay, a generalization of before, and with Kazuya, we show that again, this is true for the existence of symplectic form. It's still open for a general compass of manifold to show that, in fact, you have only the complex torus, but in this case we show, and the proof here is quite simple because it doesn't use only symplectic geometry, let's say. How a symplectic form, the behavior of symplectic form on completely solvable Lie groups. Okay, and now I report a nice non-existence result about twistor space that I will use also in the third lecture. And that's nice because it really used the relation between taming condition and pluricluse in a strong way. So let's consider compact anti-cell dual Riemannian form manifold. So it means the cell dual part of the Y tends to 0. And let's consider the twistor space. We need this condition W plus 0 because the complex structure that we will consider will be automatically integrable. So the twistor space is just a set of unit vector, okay, in the bundle nabla plus, which are essentially the 4 alpha, which are cell dual, so such that star alpha equal to alpha. And here we can use identification of the space of the bundle of 2, 4 with the bundle SOTM. So that means that the cell dual 2 form you can identify as an endomorphism. And that's a way that the unit vector here correspond, in fact, to oriented orthogonal complex structure, right, on the tangent space. So at each point of our twistor space, consider the composition induced by the Levi-Civita connection. So we have the horizontal part and the vertical part, okay? And one can define in a natural way, is not the only complex structure that you can define, I will define this one. So let's consider EMS like ES, where ES is a complex structure on the tangent space induced by S, okay, in tautological way, let's say. And then we have the other part on the fiber, which is the complex structure on that you can identify essentially with the two-sphere, and this is induced by the metric and orientation. And the nice result by Verbitsky is that if the twistor space of a compact anti-cell dual Riemannian manifold emits a pluriclose metric, then automatically it's scalar. And then by each result, it means that you can have only CP free and a flex space. I give just an idea of the proof because it's quite nice. It's using the, in fact, the result due to Campana from rational connectors of the twistor space. So it's using how is the space of deformation of the ample rational curves, which is compact. And in fact, what Misha showed that if the twistor space means the pluriclose metric, then is a Martian manifold. So it means that the algebraic dimension of your manifold is equal to the complex dimension on it. The Moisture manifold we will consider also in the third lecture related to balance metric. And so in particular, it satisfies the Dirichlet lemma. And the general property, if you have a compact manifold, we satisfy the Dirichlet lemma a dimensional pluriclass metric, then I made a symplectic form timing the complex structure. And then by a paternal result, essentially related to the condition of occurrence that I presented before, you get a contradiction. Okay, I don't know when I start, how many minutes I have here? I started 20, so I think I have still minutes, right?
Couple of minutes for sure, Anna, don't worry.
Okay, because I want to talk about the pluriclass flow and see the relation. And so let's consider now Kähler. We will have the nice lecture by Valentino about Kähler-Ricci flow, so I will just mention a few things, okay? If we start with compact Kähler manifold, so one can consider the Ricci flow. You just see the evolution of the metric. And here I forget about the factor 2, but it doesn't matter for what we are doing. And what is nice for a Ricci flow is preserve the Kähler condition, right? And the flow that you get for the metric or for the fundamental form is what is called the Kähler-Ricci flow. And in fact, by result by Cao, Tian, we see better in the lecture by Valentino, reduced to parabolic Monge-Ampère equation. Okay, what we can ask for non-Kähler manifold? Of course, the Levi-Civita connection will not preserve the complex structure, and the Ricci flow does not preserve the Hermitian condition. Someone may consider other connection, preserving both the complex structure and the metric. In particular, the bismuth connection. Also, one can consider flow related to the Chern connection, but I will not consider here in this lecture. And what is nice here, that Street and Tian introduce a geometric flow. So it's really a geometric flow because they show that it's a gradient flow of a functional. And the idea is to evolve the fundamental form, which is equivalent to evolve the matrix in this way. The T omega T is just given by minus. Here we can take the Ricci form of the bismuth connection, which is a 2 form. The problem is that when the manifold is just Hermitian, rho B is not of type 1. So one consider the 1,1 part and just consider minus rho B 1,1 part. Okay. And what is nice, of course, in general, if you don't restrict to the pluriclass metric, so if you forget about pluriclass, you don't have the short time existence, you don't have the licity of the operator, but if you restrict to pluriclass metric, you have that the operator that to omega associate this, okay, this expression, the minus 1,1 part of B is elliptic. And that's allowed to Street show essentially the short time existence. When you start with the Kähler condition, you have just exactly the Kähler-Ricci flow. So here I will present just a conjecture that is open about pluriclosed flow, was conjectured by Street and Tian. Okay, the important thing, if you look in local complex coordinate, you have just this expression. So del, the adjoint of del, the star of omega t, plus, let's say, the conjugate that, plus E, the d bar log of the GT. This is essentially the local expression of the Ricci form of the Chern connection. And here we have already linked with symplectic form timing the complex structure. Because if you ask for the existence of metric, okay, pluriclosed metric, such that the 1,1 part of rho B is proportional to omega, you can see that this is just a generalization of Kähler-Einstein condition, right? Because if you have a Kähler, then rho B is just a Kähler form. So you are asking that the Kähler form is proportional to omega. Then you have the existence of a symplectic form timing J. So one of the problems related to pluriclosed metric is to pluriclosed flow is to describe the maximal smooth existence time and study the limited behavior at the time t. So to do that, it will be important that aptly apply homology. One can define the apply homology, the real, so we are taking real form, which are IDD bar close up to del eta bar plus the conjugate, let's say, exact. And what is just, so as in the Kähler case, one can introduce the analogous of the Kähler cone, which is in this case the apply, one apply positive cone. So essentially are the apply class represented by pluriclose metric. And since the first chain class can be viewed as an element of the other homology is a homology class of what chain in this case, because something which is D close is also DD bar close. For this, you can interpret the first chain class as a 1-1 apply class. And the nice thing here, that as in the Kähler-Ricci flow, one has, since essentially you have that d t of omega t is equal to minus C1 of your complex manifold, you have that the apply class, real apply class of omega t is a combination of the apply class of omega 0 minus C1. And that's one Streets and Chian show that the maximal smooth existence time for the pluriclose flow with initial condition is just given by this tau star of omega 0. Essentially is, let's say you're looking the maximal t for which you have that omega 0, the class of omega 0 minus t C1 is in P. And they conjecture that the maximal smooth solution of a pluriclose flow with initial condition exists on that interval, 0 tau star omega 0. There are many results about pluriclose. I will mention one that I get and then maybe I will finish, probably. I don't know. For a Lie group with a left invariant medium structure, okay, in general, pluriclose flow is PDE, translating PDE equation, but for when you work at the invariant case, you can work at the level of ODE. And using the Laurel tricky, so you use, essentially you fix the Hermitian structure, and you, instead of evolving in the pluriclose flow, J is in fact fixed, okay? And G and the metric is evolved. Here you fix also the metric and you evolve just the bracket. What we show with Henriette and Vezzoni is that pluriclose is in fact defined for any T positive. And later, Arroyo Lafonte also look the convergence of the solution in the Gromov-Hausdorff sense, which is adapted in the case of nilpotent. You are not working in a compact manifold, so you have to adapt that. But what is nice is that after a suitable normalization, you get self-similar solution of the flow. There are other results related to pluriclose flow that I didn't mention on other type of Lie groups, but until now the conjecture by Streets and Chian is still open, so one doesn't know if it's true in general or not. I think I finish here, and maybe next time I will present the last part of this and I will continue with the rest. I think I overtime, right? No, probably. So I will finish here.
Thanks a lot, Anna. Thank you very much.
Thank you. And sorry if I went over a little bit.
No.
I will next time I will continue a little bit. I have just a few things that I have to say, and then we will continue with the second topic that anyway is related to this one. So yes.
Thank you. Thank you from all of us. Are there any questions? We will wait for the discussion session.
I have a
small
question, if I may.
Yes, yes.
Vincent?
Yes. Anna, so you mentioned earlier that if you are working on a pre-closed manifold and you blow up one point, then you can get another pre-closed metric on the blow-up manifold.
Yes, yes. Essentially, we adapted the proof of the Keller case in our case. Yes.
So maybe you said it, but I did not hear.
Yes.
What if you blow up a smooth center of, I don't know, complex dimension 1, for instance? Is it wrong? Do you have a counterexamples? Or?
No, we didn't have counterexample, and this is a nice problem. In fact, we don't know if it's possible now. We just proved that for complex blow up in a point on a compass submanifold, but we don't know in general. I think there are, maybe also Adriano can answer, but there are no counterexample, right? As far as I know.
Yes. No.
It's still open.
He agrees with you.
Yes.
He's here.
Yes, all right, yes.
It would be nice, of course, to have some counterexample, but we don't know.
So the problem is open, whether
The
this
problem
condition
is open, yes.
on the blow up of a higher with higher center.
Yeah, for instance, an open problem that I try a little bit, but I didn't success, is to see, for instance, if you take the Hilbert scheme of points, so a resolution of symplectic product would be nice to show if there is or not pluriclose metric, right? Because if you take just the symmetric product and you resolve, then in that case you blow up along with the diagonal, so everything is okay. But if you do higher, if you consider higher Hilbert scheme, then it's not clear we don't know if admits or not pluriclose metric. That would be also an interesting problem to see if that construction, because if you start with Keller, you get Keller, right? If you start with holomorphic symplectic, which is another thing anyway, you get still holomorphic symplectic, but it's not clear if you can see that for pluriclose metric. There is recently a nice, not recently, maybe 2 years ago, a nice paper by Verbitsky where they try to understand better the holomorphic symplectic case, and maybe one can take some idea for pluriclose case, but also that case we don't know.
Okay, thank you, Anna.
Welcome.
Another question by Mario Garcia Fernandez. You can
Oh
unmute.
yes, sorry, Mario.
Yeah, it's about this result by Street-Santian that you mentioned, that if the Hermitian form is proportional to the one part of the Bismuth-Ricci form.
Yes.
So is it? What is the idea of the proof? Is it easy to prove this thing that it admits a?
No, it's as far as I remember, is not so. Is quite straightforward. It's not so complicated. Of course, lambda has to be non-zero, because for lambda 0, yeah, you get a static, what they call static pluriclose metric, and then is another story. Yes, it's not complicated. It's just, no, it's quite easy. They use again, I think, as far as I remember, how will be the signature of the intersection form of your fundamental form, let's say, as that's and then it just, I think it's just straightforward. It's just a computation, straightforward. It's not complicated. It's in the paper by them, in the one where they introduced the first time the pluriclose metric, and they mentioned this as a Hermitian symplectic form. At this moment, I think it was a straightforward computation, just taking that and then see that the 1-1 part has to be the 1-1 part of a symplectic form. So they construct the symplectic form, essentially. from row B11.
Okay.
I have not here the paper, but I can see, and I will more prepare. But it's, as far as I remember, it's short, the proof. It's nothing complex. It's just using there is something about that also in Ivanov before them. They were looking this condition rho B11 proportional to the metric. Yes. As, but they use the fact that this is a 114, which is the 1-1 part of the Ricci form, and the Ricci form and the Bismuth Ricci form and the chain Ricci form represent the first chain class. That's what they use, as far as I remember. Yes. But the lambda 0 is another story, so it's completely different. So they use lambda non-zero strongly.
Thanks a lot. Thank you very much.
Thank you for the attention.
Stop the recording.